Good morning, everyone. I'm Bihag, and I'll be talking about some of the recent exploratory work that I've done regarding using neural networks to do parameter estimation from galactic rotation curves. So, we know that rotation curves are an important set of observations at galactic scales. In particular, they're essentially just orbital velocity of stars and gas around the center of a galaxy as a function of radius. And they can be used to understand and constrain galactic scale effects of various theoretical models. That includes models of dark matter or models of modified gravity. And this inference or this constraining is usually done using the framework of Bayesian inference. So where one uses this Bayes rule to construct a posterior, to define a likelihood, and then of course get marginal and joint distributions for these parameters. Now the question that we wanted to ask was essentially, can we use machine learning techniques like, for example, neural networks to do some sort of parameter estimation, to learn parameters from rotation curves. So I'll just briefly recap what the usual approach is. So for the Bayesian approach, we basically have a bunch of data which are just points and they have errors associated with them, and we have some theory parameters that aims to describe this data, and we set some priors for these parameters, and then we define a likelihood function where then we use Bayes theorem to define a posterior, and then we use some sort of Markov-Chain Monte Carlo techniques to sample this posterior and get some sort of a distribution, right? If we use neural networks, because neural networks are incredibly good at approximating functions, one can ask the question, okay, so if you have a bunch of rotation, circular velocities, can we basically learn a function that goes from the space of these velocities to the parameters of the model that we are trying to describe? So can we learn a function which is a nonlinear function which is f as a function of the velocities v and parameterized by something that I'll get to, right? So this is the thing that we are trying to do. And once we train this neural network to learn this relationship between rotation curves and parameters, one would give it the actual observed rotation curves and get the parameters that we actually want. Okay, so what exactly is a neural network? I'll very briefly go through this. So suppose there exists some potentially complicated relation or complex relationship between the input x and output y, and this input x and y could be vectors, could be y could be categories that we are looking for. So all we need to construct a neural network are just observed samples, basically observed samples of known pairs of inputs and outputs, x and y's, and we can construct a function f, which is a function of all the inputs parameterized by the so-called weights and biases, and the entire point of training a neural network will be to optimize the parameters omega, which are the weights and biases, such that the output of the neural network is close to the expected output. And this closeness we basically define using something called a loss function, which has to be minimized. Right, so lately there has been a lot of interest in using these neural networks to conduct parameter estimation. So there are a couple of ways in which this is done. One way is to basically speed up Bayesian inference. So instead of solving, for instance, Boltzmann codes to get CMB spectra or matter power spectrum, we basically emulate these processes using a neural network that speeds up Bayesian inference at the end, right? One can also use neural networks to mimic various parts of the Bayesian inference pipeline. For instance, to directly basically obtain the posterior, learn the posterior from using various techniques, complicated techniques like neural posterior estimators or neural ratio estimators. However, these two work within the Bayesian inference framework. Another way of approaching this is to do direct parameter estimation, the thing that I had described earlier, where you learn the relationship between data and parameters, and then you give it observed data to get parameters directly. This does not fall into the purview of Bayesian inference in some sense, and this is something that we will be looking at in a very simple scenario with a very simple neural network. And this has been recently explored by for the case of cosmological parameters from H of Z data by Shrikanta Pal and Rajiv Saha, for cosmological parameters of CMB spectra by J.G. Wang, and of course axion string parameters from CMB maps by Hagimoto and Mustafa Amin. So very quickly, galactic rotation curves are essentially, as I had mentioned earlier, circular velocity of gas or stars as a function of radius. And of course, we know that luminous mass in a galaxy is often not enough to describe observed rotation curves. So we need some additional component. So this additional component, in some sense, it could be modified gravity, it could be dark matter. We'll be considering in this talk dark matter. So basically what we'll want is an additional dark matter component which we can parameterize, added to the already existing baryonic component that has been modeled by the Spark database, and we basically try to see how close to observations we can get. Right? The dark matter model, to basically talk about, very briefly introduce dark matter. What do we know about dark matter? We know that it's non-relativistic in that its pressure is much smaller than the rest mass energy density. We know that it consists of, it accounts for 85% of the total non-relativistic energy density of the universe, or 25% of the total energy density of the universe. And we know that it has small or negligible couplings to standard model particles, except gravitationally. And what do we not know is basically everything else. If it is a particle, we don't know the mass of this particle, we don't know whether it's a boson or a fermion, and we don't know whether self-interactions of this dark matter particle are important. The model that we'll be considering in this talk will be scalar field dark matter, where we consider a spin zero boson with mass much smaller than order 10 eV, and given observations of the local neighborhood of the dark matter density in the local neighborhood, as well as a typical velocity of dark matter particle in a galactic halo, we know that if mass is much smaller than order 10 eV, the de Broglie wavelength will be much greater than the interparticle separation, in which case we can describe the collection of these particles using a classical scalar field. And this is exactly what is done in the paradigm of fuzzy dark matter, where the equations of motion in the non-relativistic weak field limit are essentially just the Schrodinger-Poisson system, where psi mod square has the interpretation of mass density. So these equations also admit steady state solutions called solitons, and if mass is of the order of 10 to the power minus 22 eV, and the corresponding de Broglie wavelength will be order kiloparsec, so we can form these solitons at the centers of galactic halos. And one have over the last 10 years, there are very interesting effects at galactic scales because of this large de Broglie wavelength that have been explored to constrain these dark matter models. And essentially what has happened is the most interesting mass range, mass of the order of 10 to the power minus 22 eV, has been effectively ruled out by various astrophysical observations. Here I have not mentioned the constraints mentioned yesterday by Professor Raghunath and Professor Shantanu as well, but that also basically constrain M of the order of 10 to the power minus 22 eV to not form all of dark matter. So the question is FDM ruled out? Well, I won't be answering that question in this talk. It will be, because all of these constraints have not considered the effect of self-interactions, which will be discussed by Gaurav Goswami tomorrow. So today we are just going to deal with this very vanilla kind of FDM model and see what neural networks can do here. Right? The parameters of interest are as follows. Because the dark matter density profile in the case of fuzzy dark matter has a flat density core at the inner regions and NFW-like halo at the outer regions, we characterize this by just a rho dm as shown in the as shown over here. So we have a flat density core in the inner region and an NFW-like envelope at the outer region, and this entire density profile is parameterized by these four parameters, which are mass of the FDM particle, a scale factor which is related to the mass of the soliton, transition radius, the radius at which the core transitions to an NFW envelope, and RS, which is just the NFW scale radius. We can tune the baryonic contribution by the stellar mass to light ratio, and we are considering dwarf bulgeless galaxies because the contribution of dark matter is greater at all radii for such galaxies. Right? The modeling for V disk and VG is already given by the Spark catalog, so we won't be touching that. We'll just be tuning how much they contribute, in particular this disk component. Right? So the parameters that we have are 5 parameters: epsilon d, ms, rt, and rs. Right? The neural network that we are looking for essentially has rotation curves as input and theory parameters as output. So what do we do? Well, we take some uniform distribution of these parameters initially, and we draw many samples from them. We solve, we obtain basically the density profile and then the theoretical rotation curve. We consider these to be our simulated rotation curves, and we use these to train an untrained neural network where the ground truth are the values of the parameters that we started with initially, right? Once this is trained, we actually feed it the observed data, observed rotation curves, and then get parameters as predictions, and hopefully uncertainties associated with these parameters is something that I'll discuss. right? This is the process of generating simulated rotation curve, and in the interest of time, I'm going to skip this. And these are the galaxies that we have considered, the 7 dwarf galaxies, and these are the uniform priors that we give to basically generate our training data. Okay, so the neural network, the architecture of neural network that we use has been obtained using a grid search for a couple of galaxies because that is quite computationally expensive to do. And we basically use 2 hidden layers and 200 neurons per layer, and we train the neural network for 250 epochs, which is a batch size of 32. And we also include this dropout parameter, and I'll not go into the details of this. But the important thing to know is the loss function. We'll be using initially a very simple mean squared error loss function, which is just the Euclidean distance between the output of the neural network and the expected or the ground truth values. The neural networks that we have will have around 40 to 50,000 weights and biases, and we'll be using around 500,000 rotation curves as our training data, which are split into which are split as 80, 10, 10 into train, test, and validation sets. Right? So once we train this neural network for 250 epochs, you see that the loss has basically settled down after 250 epochs, and we then choose a couple of rotation curves in random from the test set, a set that neural network has not seen during training, and we construct from the parameter predictions, we construct rotation curves to see how well they match, and we see that they match more or less okay, except for this particular one. So the test set is around 50,000 rotation curves. I've only shown 4 randomly drawn ones. And the problem occurs when we actually give it observed rotation curves. You can see that this is quite terrible. None of the fits are really good. So the reason for this is the theoretical rotation curve. If you see for this particular galaxy, if you just remove the baryonic components and we keep the rest and we compare it with the theoretical rotation curve, you can see that the theoretical rotation curve is quite smooth, while the observed DM contribution is quite wiggly. And this is why when we train it on this smooth curve, when we give it something that is a bit bumpy, it does not really recognize how to basically get the parameters. And you can see that where the dark matter contribution is nice and smooth and it matches the theoretical rotation curve, the predicted parameters actually give an okay fit. So what do we do to fix this? We add noise to the training data. So already rotation curves come with observed noise. So for every simulated rotation curve at a particular radius, we add an additional term, which is just a random draw from a normal distribution with 0 mean and the observed uncertainty as the standard deviation. And then we again train our neural networks for 250 epochs, and when we again give it the test set, just the same 4 randomly drawn rotation curves, and we see that it's still performing quite well. However, when we give it observed rotation curves, you can see that the things have drastically improved. The red curves are basically the predictions given by neural networks trained on noisy data, and you can see that for almost all galaxies, this is now fitting quite well with a quite low reduced chi-square, except for this particular galaxy, UGC A444, and we'll get to that as well. However, when we do Bayesian inference, we also expect uncertainties associated with these parameters. So how do we get that? So in this particular way of doing things, we have recognized that obviously observed rotation curves for the galaxy at every radius has some uncertainty associated with it, right? So what we do is to simulate multiple observations. We basically draw at every radius from a normal distribution or a Gaussian distribution with mean as the observed velocity and sigma observed as the standard deviation. So essentially taking a 1000 draws from this basically means that we have 1000 realizations of the observation. So, and then we make predictions for each of these realizations. So one can think of this as sampling from the vicinity of the observed rotation curves while being consistent with observations, right? And we basically get a chain of parameters. So this is not exactly an MCMC chain, but we basically get a chain of parameters that we can then use to plot 1D and 2D distributions. And when we do this, well, for some parameters it works remarkably well. For scale, RT and M, it does quite well. However, some of these parameters, the rotation curves are not very sensitive to. For instance, RS and epsilon star. Okay. By the way, here the blue curve, the blue shaded region are the posteriors for the MCMC approach, and the green shaded regions are the not posteriors but 1D and 2D distributions for the ANN approach. And you can see that for these two parameters, where they are not very sensitive, the rotation curve is not very sensitive to them, this approach completely fails. So we need something else. And this is just I'll just skip this for now. So how do we learn uncertainties better? Well, what we ended up doing was using a different loss function, which is called a heteroscedastic loss function, or sometimes also negative log likelihood in machine learning literature, where we basically introduce this additional parameter sigma ij, which the neural network can predict, but it has no ground truth value, right? So if the neural network predicts a very large sigma ij for any particular parameter for any particular training data point, this term will blow up, basically making the loss very large, so it will have to reduce it. But if it reduces it too much, then this term will blow up, and again, so it will have to increase it. So looking at the training data, the neural network will automatically learn during training itself the uncertainty associated with every prediction that it makes of the parameters. So when we do this, you see that using the MSE loss function and the multiple realizations method, the median values of the multiple realizations method, and the comparing those to the predictions obtained by the heteroscedastic loss function, you can see that in fact heteroscedastic loss function works even better. The chi-square values for almost all of these cases are smaller. And when we compare our uncertainties to the uncertainties obtained from the MCMC approach, you can see that the purple curves, the purple whisker plots are essentially neural networks trained on mean squared error plus multiple realizations. The orange plots are neural networks trained on heteroscedastic loss, and the green plots are the parameter values and the uncertainties obtained from MCMC approach. And you can see that for these two parameters, which were hard to learn for the MSE plus multiple realizations approach, this actually, the heteroscedastic loss function actually works quite well and predicts larger uncertainties as expected from the MCMC approach. So what we have essentially learned is that neural networks require noisy training data when we are dealing with rotation curves. And of course, the MSE plus MR model does not really work well, while the heteroscedastic loss model works quite well, but it does not really predict any posteriors. That's one of the drawbacks that we are working on. And the other thing is, we don't really know exactly what the heteroscedastic loss function is learning, because this is not exactly a Bayesian approach. It's not clear what these uncertainties exactly are, but they see the values that we obtain are still similar to the values that we obtain from a typical MCMC approach. And of course, our neural network architecture has not been optimized completely. We think that if we optimize it further, we can improve the speed. And physics-wise, it is important to note that no single value of small m satisfies the rotation curve for all galaxies, which is what we would require if we have a fuzzy dark matter model. We are working on developing a joint analysis method where we train multiple neural networks together to get a single value of m at the end. That's something that we are working on. And also the values of m obtained, which are of the order of 10 to the power minus 23, are in tension with many other bounds obtained from, let's say, stellar heating or Lyman alpha data or soliton-Hilo relation or 21 centimeter observations, basically everything. Of course, the inclusion of self-interactions or multi-field dual can drastically affect these constraints, and that is something that I'm leaving for future work. Yeah. Thank you.
Thank you for finishing in time. Time for questions.
So the sigma square observed is going to be different for different galaxies, right?
Yes.
So how is that included in the training set?
Yes. So that's something I did not mention. We train a different neural network for each galaxy.
And how time consuming is that?
That's so on my laptop it takes around 40 minutes to train a neural network.
And MCMC?
MCMC takes around 30 minutes for the entire thing. So here I'm not even counting the generation of training data, which takes time. That's why the optimization of the neural network architecture will improve the speed further.
Okay, thank you.
Yeah.
Can you go back to the previous? Yeah.
This one?
Yeah, this one. So you see you get a two-sided error bar, which means your data prefers an ULDM mass. It's not an upper bound or lower bound. And you see it where, as you pointed out, you see each galaxy preferring a different value. Isn't that a sign of some missing systematic in your model?
I see what you mean, right?
It's not just here, like, there are SIDM papers with similar plots.
I see.
And that seems to me to be a sign of a missing systematic.
Okay, that is something that we have not considered, but I'll think about this.
Yes. Ranjan.
Hi, Vivek. Thanks for the very nice talk. So I may have asked you this question, but I have forgotten the answer. That's my fault. So if you do multi-field ultralight dark matter, do we know? How the multi-fields will be distributed inside the galaxy? Is there any theoretical studies about?
So there have been some recent simulations by Box
Marsh.
and others.
Yes.
They basically, the density profile will be, so the inner region will be dominated by the heavier mass, and the outer region will be dominated by the lighter mass.
So then it's just NFW, right? Because the lighter mass will do the solitron at the center, right? If you put
No, so it will be a two soliton kind of a thing, where it will have a flat thing, it will go down, and again have a flat thing, and it will go down.
Okay, thanks. Thank you very much.
Rajiv.
So in the Bayesian framework, you typically want to ensure that your posterior is not prior dominated, right? You're not computing any posterior here.
Yeah.
How do you ensure that in this framework?
So that we do not really do that.
So then, how would you actually go about and trusting these constraints?
So so what we have essentially done is compared it with the standard MCMC approach, right? So the benchmark that we have set is, okay, if MCMC with the same prior is giving you this, can neural network reproduce that?
Hi, Bika. Thank you for the nice talk. Just a follow up on the first question you said. For like in your training data set, you have multiple rotation curves. For each rotation curve, you said you'll train different neural networks, is it?
No, not for each rotation curve. So for each galaxy, we have a different neural network.
Sure.
And we have around 500,000 rotation curves for that particular galaxy. So simulated rotation curves.
But finally, like when you have like some test data, like when you have some real data or some unknown thing, like you have to pass it through like a single network.
Yes, we pass it through a single network.
Okay, thank you.
So just a clarification again related to the earlier question. So maybe I missed this. So can you tell me what is the parametric dark matter profile you're using? I mean, people have used different in literature.
It looks something.
No,
something
the
like
dark matter. Okay, so
that. Yeah, this is the dark matter density profile.
okay, so people have used a fourth model which scales as the inverse fourth power at low distances. So have you used that? And at NFW at larger distances?
Yeah, so we have used this in the inner region.
Okay.
Yeah. The shift profile.
Okay, fine. Okay, thank you.
Okay, let us thank Bihag once again.
Thank you.